forward. Okay, so we've been waiting for JWST for a very long time. It has pulled the oxygen out of the room for astrophysics for a decade in terms of getting other missions going. And it is going to be, I think, a spectacular mission for all branches of astronomy. I'm going to focus in not just on exoplanets, but actually much more on direct imaging, where I think it has a modest niche compared to, I think, what we'll see with transits from what Nicole was talking about, and I'll talk a little bit about that. Just for reference, as Courtney showed, a TESS mirror is about that big, a Spitzer mirror is about that big. This is a pretty big telescope. So we've seen this many times. This is sort of the graph of where planets are in period and mass. The transit follow-up arena for JWST is in here, and the imaging searches and follow-up will take place in this range up in here, of order probably 10 AU for the closest stars, and masses that actually will go down well below a mass of Jupiter, given the sensitivity of JWST in certain kinds of stars, and that's really what I'll focus on. So I'll put this in the context of the NIRCam team, of which I'm a member. Marcia Ricci is the principal investigator. And so we have a subset of the NIRCam team which is going to focus on exoplanets. And what we're going to be doing is really covering the waterfront to try out various aspects of JWST in different arenas of exoplanet science. You can either accuse us of taking the lowest piece of fruit on each of the cherry tree, the apricot tree, the peach tree, and the apple tree, and to a certain extent it's true, but we're also doing this to try and explore the instrumental capabilities of JWST. So we have a program joint with the MIRI team, that's the mid-infrared camera, to image known young planets. There'll be direct spectroscopy of more widely separated planets. That'll be joint with probably the NIRSpec spectrometer team and the mid-infrared team. Nicole talked a lot about the transit spectroscopy of known planets, and there's really quite a broad integrated program across all the instrument teams, mission scientists, and so on. And they will do a pretty small number of objects, but we hope to do them pretty exhaustively with all the instruments. So we do a few planets well. There'll be many more planets for people to do after the instrument teams have done some stuff. We're hoping to have a coronagraphic survey of young M stars. Probably that'll be just the NIRCam team working in conjunction with the Canadian NIRIS team, who have a non-redundant mask I'll talk about in a minute. And certainly an interest that I have is that some of the coolest brown dwarfs are really analogs to exoplanets. These are 5, 10 Jupiter mass objects that are free-floating, but we have the ability to study them in great detail spectroscopically and use that as a forcing function for exoplanet models. And indeed, the hot ones may be analogs to the young planets that we're seeing as well. So just talking first about the imaging. When I first started working to help develop the coronagraph for JWST for NIRCam, I went to a couple of the guys who were working on the coronagraph for what was then the terrestrial planet finder coronagraph, where the wavefront errors were something like 1 nanometer of wavefront error. And they were really excited showing how we could get down to Earths. Carl was working on things like that, John Trauger. And I said, oh yeah, by the way, our wavefront error is something like 130 nanometers. And their response was, buy a piece of black tape, put it over the star, and don't bother me anymore. And if you're working with something like TPF, or you have an extreme AO system on an 8 to 10 or ground-based telescope, you've got a smaller wavefront error, maybe 10 to 30 nanometers, and a better inner working angle, bigger diameter telescope, more sophisticated mask designs. But JW brings two things to the party. One is it's highly stable. We believe that in going from a target to a reference star over a few degrees, over a few tens of minutes, the stability in your point spread function will be something in the range of 5 to 10 nanometers. And then as you move out into the mid-infrared, the background, once you get a little bit away from the star itself, say outside the central arc second, the background just continues to drop to being essentially negligible, so you get great sensitivity. And so that's what we'll be taking advantage of. So this is the NIRCam chronographic masks. We have some spots, which are sort of 6 lambda over D spots from 2 microns up to 4.5 microns. We have some wedges where you can work in sort of a one-dimensional way to as close as 4 lambda over D. These are good for broad searches. These are good for where if you know exactly where your planet is and you want to optimize your contrast at either 2 or 4 microns. And these are sort of the inner working angles you can hope to work at. MIRI, the mid-infrared camera, has a different kind of mask. They use what are called 4-quadrant phase mask chronographs. You put the star right here at the center at 3 different wavelengths potentially, and by changing the phase by pi over 2 across each of these squares, you can block out the light from the central star at the level of something like 10 to the minus 4. And then finally, the Canadian NIRCam instrument has a bunch of masks that you place onto the pupil image of JWST. These are non-redundant baselines spatially and in an angular sense, and you get a nice sampling in the UV plane, and thus you can get a very high spatial resolution, essentially lambda over D over 2. So instead of 4 or 5 lambda over D, you're operating at a half lambda over D, so a much better inner working angle. You're confined to the aperture here, so you have also a constraint on your outer working angle, but within that specified range, you actually get a 5 to 10-fold improvement in inner working angle compared to a traditional coronagraph. So we can put all these on a plot to sort of get an idea of where they all fit. So here's NIRCam at 4 microns using our spot. So at 1 arc second, we're maybe at something like 10 to the minus 5. Not as good as, say, Keck with its vector vortex, which goes into a closer inner working angle, partly because it's working at 3 microns, but also it's just a better design, more up-to-date design mask. And so in here, this might win until, as you get out beyond an arc second, for Keck or any ground-based system, you hit the thermal background floor, whereas for JWST, you just keep gaining more and more sensitivity. MIRI's up here at 11 microns, sort of 10 to the minus 3, 10 to the minus 4 rejection, but of course the star is fainter and the planets could be brighter, so there's more of an advantage there. The non-redundant mask in the nearest instrument is probably going to get to something like 10 to the minus 4 inside this very in-close region around this small inner working angle. Not as good as things like GPI or Sphere or eventually TMT or one of the other big telescopes at shorter wavelengths, but the planets are very much fainter here. They're very much brighter up in here. So there's certainly a niche for direct imaging with JWST. Why are we interested in JWST for direct imaging? This is a plot, I guess, that one of Adam Burroughs' students put together showing a spectrum for HR8799C, and you can see how rich a spectrum we actually have in terms of a whole range of different molecules with different assumptions about what the clouds might be, clear, non-equilibrium chemistry, different levels of clouds, and so on. And up at the top, we have the different filters for NIRCam, MIRI, and the range of the NIRSpec spectrometer. Now for close-in systems like this, we don't get to do spectroscopy. We just get to do work through the various filters, and I'll show that first. For more widely separated planets, we actually hope to be able to do some direct spectroscopy. One of the things that is important about exoplanets is, particularly the ones that we're imaging, is their formation mechanism actually affects their appearance, and their physical properties are considerably different depending on whether they formed through a disk instability, a high entropy hot start, or a core accretion, sort of more like a star formation process but on a very long scale. And there are just differences here in the initial entropy that fade as a function of age. By the time you get to 100 million years, these lines have all pretty much merged together except for perhaps the very largest planets. But in terms of radius, temperature, or luminosity, there's quite a big difference between the two. And we hope to be able, from these observations, to recover that kind of information and distinguish between formation in a disk versus core accretion or disk fragmentation. So what do some of these planets look like? These are some models from Adam Burrows and his student Spiegel. And we have here going out from 1 micron all the way out to 15 microns. Here's the NIRCam filters, the MIRI filters. And you can see there's obviously a lot of action going on out here. Not so much activity here, at least for these warmer objects, but these are the wavelengths where you can get a very good handle on the total luminosity of an object. And once you have a luminosity and a temperature, you can get to a radius. And that, of course, is one of the fundamental things you'd like to get for these planets. Let's zoom in a little bit to the NIRCam filters. And we're trying to choose filters that let us go in and sample these regions in the spectrum and delineate specific features in here, and then use that information to recover properties of the planets. So in planning the NIRCam program, we want to be able to go in and choose what are the right filters, what is the minimal filter set we can get away with. And to do that, we went through a process that I would call unabashedly frequentist. And I've learned that I can't do that anymore, so one of the things we'll try and do is actually, as we work to analyze the data, we'll be taking much more of a more modern approach. I would say, however, the biggest problem is still going to be, what are the actual model sets that one is going to work with? I mean, there's still, as you'll see, quite a lot of uncertainty in what the models really convey about these planets, and that's going to probably be the biggest challenge in our interpreting them. But in any event, in this case, we took the Spiegel and Burrows models. We ran a sequence of Monte Carlos over a range of filters and planet properties. In these cases, we know in principle the age of the planet. It's the age of the star. These are in typically well-known moving groups. The age may itself be uncertain, but at least we can fix that as a parameter for now. We assume a detection range of an SNR ranging between 5 and 25 based on the filter and the amount of observing time we're willing to invest. And we looked at different sequences of NIRCam and MIRI filters to find the best suite of filters to recover things like the input mass, the initial entropy, the model atmosphere, clouds, composition, and so on, while minimizing the total amount of observing time. And then we want to assess how well we can fit the input planet parameters. So this is just a quick snapshot of sort of the masses and ages and initial entropies of the planet model, effective temperature, luminosities, radius, and so on, of the models that we took. So if we took like 2 MIRI filters and 6 NIRCam filters, they're just listed here, 10 and 11 microns for MIRI, and then between 2 and 4.5 microns, we were able to actually recover the atmospheric model pretty effectively. More than 75% of the time we'd pull out the right composition and cloud properties. There are 4 or 5 different models in the suite. We were able to recover the initial the input mass with an uncertainty of something like 10%, 8%, and the initial hot start versus cold start entropy to, again, about 10%. So that was encouraging. That's a large investment of observing time to do all those different filters, although these planets are pretty bright. So in fact, you can pick up a filter without too much incremental cost. These are just some chi-squared diagrams showing, I guess this is mass and I guess initial entropy. So we just put these in here. This is what, oops. So this is what we'd input. This is what we got back out. This has got a larger uncertainty. This one matches very well. This one matches very well. Here's a case where it didn't match so well. But we went through and tabulated all of those and were able to come up with a filter set that we thought was pretty good. This is just showing fits to the various models. We put in 5 Jupiter masses, 20 million years old, one particular model, 10 parsecs away, and we recovered pretty close to the correct values. Same thing, just zooming in on the NIRCam filters. We did pretty well in that particular fit. One Jupiter mass system, again, we have lots of signal to noise on even a 1 Jupiter mass system, 25 million years old. So if we drop 1 or 2 of the filters, we can still do pretty well. We get masses and initial entropies and so on to within about 10%. And this is likely the filter set that we'll be using in conjunction with the MIRI team. If you just take a NIRCam 2 MIRI filter set, you start to lose your ability to do the discrimination, and your mass and entropy uncertainties certainly start to grow. So we'll be going with something like a 4 or 5 filter set. So from the breadth of the wavelengths, we're certainly able to calculate, just to measure the total luminosity, derive the temperatures. We should be able to get radiuses to a few percent. To a certain extent, this is pretty model independent, because you're measuring this, you're getting a pretty good measure of that just by putting fairly simple models through a large number of data points, so we should be able to get a pretty decent radius. We're still looking at how well we can distinguish between the various atmospheric models. So what are we actually going to do? We'll probably have enough observing time to look at 5 known planetary systems. We elected not to do a large survey. Teams like GPI and Sphere are doing all these surveys and finding not a lot of planets. At $1 billion a minute for JWST time, we don't think that's a very good use of the telescope, so we're going to follow up on known systems. We will, however, look around the vicinity of these fine known planetary systems and use our sensitivity to push down for masses well into the Saturn range. And our targets will be selected to be something like 0.4 arc seconds out to about 3 arc seconds, and masses below about 13 Jupiter masses. And these are sort of the phone numbers of the planets we're presently looking at. They're typically nearby. There's some A stars, some F stars, 1 M star, 1 G star. 51 Area B is in pretty close. This may be one that strains the coronagraph a little bit, certainly at 5 microns, but we have some hopes to be able to do something there. Can we go fainter? The answer is yes. So here's the signal to noise at 4 and 3 microns for a Saturn orbiting GJ 504. And once you get outside of 1 to 1.5 arc seconds, you're starting to be able to pull out Saturn mass systems, or in fact, obviously even lower. This is signal noise of 50 in a 900 second observation. Yeah, 900 second observation. So if there are lower mass planets at larger angular separations, we should be able to pick them out. And the 2 filters that we would use serve to eliminate background stars and in most cases background galaxies. You typically expect to find the planet at 5 microns, 4.5 microns, but not at 3. There is a potential astrophysical false positive of a 3.5 micron dropout extragalactic object. That would be at Z of 20. That would be boring. We would give that object to the cosmologists. Direct spectroscopy, of course, gives you a lot of data on these systems. Quinn Konopacki did some very nice work using Keck and the integral field unit on HR 8799b. You actually are getting real spectra using the OSIRIS IFU. For more widely separated planets outside of about 3 arc seconds, you'd put the planet off to one side of the IFU, assuming the scattered light is not too much of a problem. And then you're starting to get resolutions of 3,000 spectra of some of these planetary systems. And there are some that we believe are planetary mass objects that we should be able to do this work on. Again, maybe half a dozen or so known so far. We heard a lot about the transit work, and it really will be quite spectacular. The NIRCam team, as I mentioned, with the other teams, will work to do both transit and eclipse spectroscopy, covering sort of the full range of 2.5 or even shorter spectral regions. But in particular, at this range here, we get things like methane, CO, C to 2, the Miri bands, ammonia for some of the cooler systems, 20 Earth masses up to a few hundred Earth masses, Neptunes up to Saturns, probing a variety of atmospheres, hopefully being able to see through the clouds at longer wavelengths. And that, I think, will be probably the most productive mode of JWST for exoplanets. It's really going to be unprecedented. We didn't have real spectroscopy in the mid-infrared during the explosive growth of transits, just because this Spitzer spectrometer ended with the cold part of the Spitzer mission before we really had a lot of good targets. And we'll be exploring this whole new regime with JWST. Sort of just a list of everybody's favorite bright systems. We do want to study fairly bright targets, so the K magnitudes are certainly 10th or brighter. And there's a lot of information in the talk that Nicole gave and online about the transit stuff. But these are the sort of things you have to look at. Do you want to see the geometry in a mission or in transit? Which modes do you want to look at? What are the particular features that you're looking for? And just put together something like a coherent program. There'll be lots of planets and lots of instrument modes for all of you to be thinking about and trying to understand, is there a spectral feature in my data? I mentioned at the beginning an M-star survey. This is something that Mike Meyer and Josh Schleider, who was at Ames, is now down here at NExScI, wanting to explore the sort of interesting result that that Courtney and Dave Charbonneau found with Kepler, that there are abundant numbers of small planets orbiting M-stars, at least in the transit regime, and then the microlensing result that Scott and Christian talked about, that there are abundant Jupiter mass planets orbiting at fairly large separations from their stars, or possibly free floating. So the idea is to use NIRCam coronagraphy to get down into the Uranus mass range for the youngest, closest planets, those within about 15 parsecs, that we can attach an age to based on their association with various moving groups, just from their kinematics. So the idea would be to probe about 10 to 15 AU region, roughly where the CO snow line is located. That would be favored for the formation of ice giants. And we would just look at a fairly small number of objects, again using the sort of the 3 and 4 micron filters. I think we'd be able to improve the target list from what we show up in here, which is sort of age versus distance diagram, again for the closest M stars. We tweak this with Gaia, and the work that Mike Meyer and Josh did shows that we can get down well below the Jupiter mass range for separations of 10 to 20 to 30 AU. This may be a void in where planets are indeed to be found. It depends a lot on how you form planets in disks around these low-mass stars. But even if we find just one or two objects, it'd be quite exciting. And this is a sort of a representative sample of minimum, median, maximum ages, typical brightnesses of the M star and Ys, typical distances. So we're probably going to include that in the program. We also have a program to do nearby T and Y dwarfs. These are very cool objects discovered by the WISE satellite. They're basically 5 micron only objects, 500 Kelvin. Some of them are as close as 2 parsecs away. One of the ones found by Kevin Luman. These are mature objects, 3 to 5 gigayears based on their space velocities, leading to interpretations of masses of 5 to 10 Jupiter masses. Scott and Christian, showed this. There's this bump in the microlensing curve, and the question is, if these are runaway planets, are the Y dwarfs at the sort of the 5 Jupiter mass range, sort of the tip of this iceberg? We think probably not, but we don't really know yet. That's one of the areas where microlensing and the studies of these objects very close to us may be quite synergistic. So again, there's just a lot of spectroscopy you can do with these objects. We'll take something like the 10 closest and brightest, look at them at very high spectral resolution. We'll also do companion searches using NIRCam and the nearest non-redundant mask, getting into sort of half an AU for the nearest systems. Here's a WISE color absolute magnitude versus a J minus 5 micron color. Some of these make sense in terms of fitting along a sequence. It goes down to a temperature of 220 degrees. I mean, this is a self-luminous object that's colder than room temperature. This is a white dwarf companion. This is some very squirrely object that we've been studying for a while with WISE. Its spectrum makes no real sense. It's very bright here at 5 microns, and the models have a very difficult time fitting what's going on at shorter wavelengths. Is there a lot of dust in this object, a lot of clouds? We don't really know, but being able to get a lot of detail in the spectroscopy will help a lot. So this is just an eye chart listing what some of the objects would actually be, and you can see we're focused on these objects that are very cold temperatures. I mean, these are the similar temperatures to the warm transiting systems, but here we get full spectroscopy at resolutions of 1,000 to 3,000, integration times of just a few hundreds of seconds, so signal noise of 100 for an object at 5 microns. In just 100 seconds, we get 2,700 or 2,700 spectroscopy on these things. This will do a lot to force the models to deal with these cool temperatures, and I think be much richer spectra than we can ever get for the transiting planets, but will be able to drive the modelers to really up their game in a very significant way. So this is an illustrative NIRCam program, and I put it up only just to give you an idea of what, in terms of hours, it would take to do the kinds of things I've laid out. I mean, if we want to do 5 objects with NIRCam and MIRI, it's something like a 50-hour program that gets you a full filter photometry of all the planets in a system, plus go deep to find Saturns. A direct spectroscopy program of 5 to 10 objects might be a 20-hour program. We'll spend a lot of time investing 100 hours or more from NIRCam, plus comparable amounts from the other instrument teams to do 10 objects in transit and eclipse spectroscopy. A 15 object survey with just the NIRCam coronagraph would be something like 50 hours. A Y dwarf survey, 10 objects, 40 hours, and this might total 250 hours. Realistically, it probably totals more than that with all the overheads. These numbers will come down. We might have to lose one of these programs, but the goal is to try and do something like this, But as you're thinking about different kinds of exoplanet science you could be doing, this gives you an idea of the scale of program that is possible. And I put this chart up. I don't know if Nicole showed it. It just gives you the timeline for JWST in terms of here's a launch, and now we start backing up in time. The GTOs, their call for proposals is in January. We have to submit our proposals with targets in April. There's an early release call for proposals in here, finalized here after the GTOs have specified their targets and some preliminary vetting has been done. So early release science is meant to let people get data that will come back very quickly right after the launch of JWST. So you can really start to see data early and in time, in fact, to illuminate cycle 2 proposals. And so this is really one's first opportunity, which is less than a year from now, to start thinking about proposing for JWST. So I think we'll do a lot in terms of characterizing exoplanets by direct imaging and spectroscopy of young systems going down to Saturns and up to a couple of Jupiter mass systems, transit and eclipse spectroscopy, super-Earths to Jupiters, T and Y dwarfs as exoplanet analogs. And as I've said at various public forums, exoplanet science is one of 4 main goals for JWST. They talk about the early universe, the assembly of galaxies, sort of star formation, sort of galactic science, and number 4 is exoplanets. So if there's 4 goals, that means exoplanets gets 25% of the time. That depends on writing great proposals with the best teams, the best targets, the best models, and as we've been discussing here, the best statistical methods. So I urge you to think about writing proposals, and in the acknowledgments in your proposal, don't forget to thank the Sagan Summer Workshop. Thank you. I think Spitzer gives us some idea of what that is likely to be, from some of the deep surveys they're doing. I think the advantage of having the 2 filters is we will be able to eliminate an awful lot of those objects just by looking at their 3 to 5 micron color. Typically, the Saturn mass systems won't be emitting at 3 microns, so we'll have 5 micron only objects. And I think that's likely to be rare unless, as I say, it's a 3 micron dropout. Anything that looks interesting at that point as being a very steep 3 to 5 micron color or just 5 microns only, then becomes something we have to follow up 6 months later and use a parallax or common proper motion to eliminate it as a confusing object. It shouldn't be, certainly all the stars will be simple to eliminate. Most normal galaxies will be simple to eliminate. Pathological galaxies, you may have to work a little bit harder. So what are the current
challenges from the point of view of modeling?
For the transit models, yeah. So what are the challenges in terms of the modeling of the exoplanet atmospheres, in terms of transits, then by extension, other techniques? I think you've heard quite a lot from Nicole and Mike Line about where that state-of-the-art really is. I think the first challenge is simply getting good, reliable data out of the instruments. That's an enormous, challenge that, we've heard quite a lot about. After that, it's really, do you have, depending whether you want to do forward models or take models and fit them to the data, there's a lot of uncertainties. I think clouds are probably the biggest problem. The fact that I think it was Nicole who showed the picture of Jupiter that had, 5 microns. It has hot spots, there's cold spots, there's red spots, there's spot spots. These are not single dimension objects, and things like some of the colder objects, as you get below 500 degrees, you get into a very different regime of chemistry. So the cold planets, there's a lot of different things going on, and the models for the Y dwarfs, and to a lesser extent the T dwarfs, fail by orders of magnitude to fit the data. You can either fit them at 5 to 10 microns, and then, as I showed you for WISE 1828, your predictions at short wavelengths are literally off by an order of magnitude, or you fit the ground-based JH and K data, or J and H data, and you can't fit the 5 micron data. And that, I think, has to do with clouds and the two-dimensional nature of some of these systems, where in some spots you're looking down very deep into the atmosphere of the planet, and in other parts you're looking up at the surface and you're seeing a combination of those two. So I think those are going to be the things to worry about. For the hot Jupiters, you also have things like, insolation. A very high degree of insolation causes photochemistry that needs to be taken into account. So there's a lot of stuff going on that's going to, I think, keep people very busy once we get good data. And we will have fabulous data. Start writing your proposals.